So in this quick tutorial, I'm going to teach you how to read Earth observation data from radar satellites in space. But let's first talk about why you might opt for radar imagery over optical imagery in the first place. Now, one of the biggest reasons to choose radar, and specifically SAR, which is synthetic aperture radar imagery, as your sensor of choice, is that it works outside the visible light spectrum, out in the microwave portion of the electromagnetic spectrum right here. Now, depending on the satellite, that could be X-band, C-band, L-band, S-band, or P-band, and these just refer to the different wavelengths from a few centimeters right here to tens of centimeters over here. So why does the band matter? Well, shorter wavelengths like the X-band give you finer spatial resolution and are great at picking up small surface details. Think things like crop structure, urban features, or ice roughness. But they don't penetrate very deep into the vegetation or soil. Now, longer wavelengths like this L-band here can punch through a forest canopy and give you information about the ground or tree trunks underneath, or it can penetrate even a little into the sand or soil as well. So the band a satellite operates in isn't a small technical detail. It essentially determines what the radar can actually see, if you will. But regardless of band, all radar shares one huge advantage, because it's an active sensor sending out its own energy and then measuring what bounces back. So it doesn't depend on sunlight, and its wavelength is long enough to pass through clouds, and that means that radar can see through cloud cover and operate in total darkness. Optical imagery, of course, on the other hand, is passive. It relies on reflected sunlight, so it needs daylight in clear skies. And a huge amount of the planet is covered in cloud on any given day. Cloud cover is worst in the tropics and along the equator, the intertropical convergence zone right here, as well as coastal regions, monsoon belts, and places like Southeast Asia, Central Africa, and the Amazon basin. Now, in some of these regions, it's common to wait many days, sometimes even weeks, for a single cloud-free optical pass over your area of interest. So for example, here in Nebulum, which I've linked to below if you want to follow along, I have the default base map shown here on page load. Remember though, that this layer isn't time-stamped. It's just a clean, high-res, cloud-free tile set of the region for reference. Now, if we want time-stamped data, we need to go over here to one of our time-stamped layers. So for example, I can select any of these time-stamped satellite data layers here, and for demonstration purposes, I'll select this time-stamped optical layer right here. Now notice, after I do that, in the date picker element up here, we can now see cloud coverage represented by color. So for example, here we see these green dots, which means low cloud cover, and these red dots mean high cloud coverage. But what if we needed satellite data on these days that have high cloud cover? So this is the case, or one of the cases anyway, where you would use radar satellite layers instead of an optical layer. Now, traditionally, radar satellite data comes back as grayscale, just black and white. But within Nebulum, you'll also see some false color radar options here as well, which give you a different way of visualizing radar backscatter. Now, we'll talk about backscatter in a moment, but for now, just notice that this is the exact same map that I showed you before as an optical layer, except now we've cut through the cloud cover and now we have full coverage of the area of interest. Okay, so now we know that radar can cut through clouds and see in the dark, but what do the different values between white and black actually mean? With no color information coming back from the raw sensor, we're left with a grayscale image, and the brightness at each pixel represents backscatter, which essentially is how much of the radar's own transmitted signal bounced back to the satellite. Now, a few things determined whether a spot on the ground shows up as dark or bright. First, we have surface roughness, which will be relative to the radar's wavelength. So smooth surfaces, things like calm water, paved roads, flat bare ground, almost act like a mirror. They reflect the radar pulse away from the sensor in a specular bounce. So very little energy returns and the pixel shows up as dark or black. Rough surfaces scatter the signal in every direction, including back towards the satellite. So they tend to show up a little bit brighter. Another thing that will have a huge impact on the brightness of the pixel will be the geometry, especially corner reflectors or angles that are at 90 degrees. So when two hard flat surfaces meet at a right angle relative to the radar, Imagine something like a building wall meeting the ground or a ship's hull and deck. You get what's called a double bounce return. The signal bounces off one surface and then another, and then it goes straight back up to the sensor. Now, this creates an extremely bright, almost saturated pixel. And this is why buildings, bridges, and metal ships light up so distinctly in SAR imagery. And then at a more advanced level, we also have things like dielectric properties. So basically things like moisture and material. Now, water content strongly increases how much energy a surface reflects back. So wet soil, saturated vegetation, or moist ground scatters more strongly than dry material of the same surface roughness. Metal is also highly reflective to radar, which is part of why man-made infrastructure stands out so clearly. So, in short, flat, dry, and calm surfaces tend to be darker. Rough, wet, or angular man-made surfaces tend to be brighter. So why does this matter? Well, it matters because once you understand what's determining the returned pixel brightness, a grayscale radar image can provide a huge amount of value. So here are a few real-world use cases. So first up, we have oil spill detection. So oil flattens waves on the ocean surface, making it act unusually smooth to radar. So spills show up as unmistakably dark patches against the rougher, brighter open water around them. Next up, we have flood mapping. So floodwater over normally rough terrain, so things like fields or streets, suddenly look glassy and dark, making it easy to map flood extent even at night or through storm cloud cover. So next up, we have illegal mining and tailings ponds. So new tailings ponds, which essentially are just the waste that a mine generates, will show up as dark, smooth patches where there was previously rough vegetated or bare ground. And because radar isn't blocked again by clouds, you can track how quickly a site is expanding even in regions, again, with a lot of cloud cover, which is exactly where a lot of illegal mining happens. Another use case of radar imagery is deforestation and land cover change. So clearing a forest changes both the roughness and moisture signature of a patch of land. So change detection between two radar passes can flag clearing activity pretty quickly. Next up, we have ship and vessel detection. So metal hulls on open water are a textbook corner reflector case. These are going to be bright targets against dark open ocean background, which is why SAR is widely used for maritime surveillance and illegal fishing detection. So that's the core idea. Essentially, radar trades color for the ability to see through anything the atmosphere is going to throw at it. And backscatter brightness is the language that you're going to need to learn how to speak in order to read this imagery. So if you found this valuable and you have a use case for radar imagery within your own operations, you have a couple of different ways to get started here. So first, if you're looking for a self-serve option, just head over to Nebulum and sign up to access any of our Earth intelligence layers. After signing in, simply visit or create your own area of interest, select this layer button right here, and then search for radar, and you'll see all of our radar satellite options right here. However, if you're part of an enterprise team, if you're an investor or an operations manager who needs a specific answer without the overhead of processing raw satellite data or doing all of this yourself, we can handle all of that heavy lifting for you over at Nebulum. Beyond our standard self-serve platform, we partner directly with organizations to build bespoke Earth observation intelligence solutions tailored exactly to your unique workflows or white-labeled requirements. To discuss a custom project or enterprise partnership, just click on the contact link over on our website to book a briefing with us today. So that's it. Thanks for watching, and don't forget to like and subscribe to stay up to date on the latest in Earth observation data and analytics. Take care.